So good afternoon and welcome to the dissertation oral defense of Randall Holmes, who most of you know and I assume like, as we all do. His topic today is strategies for managing naturally occurring contaminants in groundwater basins of the Central Valley in California. My name is John Wyatt. For those of you fortunate enough to have not met me yet, I'm a professor in management science and engineering and energy science and engineering in the New School of Sustainability, and also a senior fellow at the Precourt Institute for Energy. I want to start by reading the Stanford Land Acknowledgement, which we're supposed to do at all official events at the university. We recognize that Stanford sits on the ancestral land of the Muwekma Ohlone tribe. This land was and continues to be of great importance to the Ohlone people. Consistent with our values of community and inclusion, we have a responsibility to acknowledge, honor, and make visible the university's relationship to Native peoples. This is a theme that, of course, is not only popular now on campus, fortunately, for us all, but also in our state and in our country even nowadays. So I greatly appreciate the opportunity to read that segment. So the examination committee, I'm just kind of the convener, coordinator, moderator of this. It's probably too an august title for someone who does this job, but I'd like to first introduce the two principal advisors, as is the custom in the E-IPER program: Scott Vendorf, the Terry Huffington Professor of Earth Sciences, Senior Associate Dean for Academic Affairs, Senior Associate Dean for Integrative Initiatives, and Senior Fellow at the Woods Institute, and probably a few other things I'm leaving out. Secondly, but that would take too much time. Richard Dick Luthi, who's the Silas H. Palmer Professor of Civil Engineering and Professor by courtesy of the brand new Department of Oceans. I did notice earlier this week, Dick also received the very prestigious 2023 he's the 2023 winner of the Perry L. McCarty Founders Award from the Association of Environmental Engineers and Science Professors, so kind of acknowledged by his own community, which I think are some of the most meaningful awards one can win in a career, an illustrious careers like his. Next, we have the kind of rising stars in the school and in the department: Gabrielle Wang-Perotti, Assistant Professor of Earth System Science and a Center Fellow at the Woods Institute for Environment, up here in the first row. And then somebody I haven't met previously, Samantha Ying, who's Assistant Professor of Soil Biogeochemistry and co-director of the UCGHI Planetary Health Center, which sounds quite relevant, at the University of California, Riverside, and I understand from the web and your comments before, a Stanford alumni. Is that correct? Yep. And then I'd like to mention that we either have or might soon have on the line online, Christina Babbitt, who's a water stewardship lead and enterprise sustainability fellow at Starbucks. She was an early mentor of Randall's in the first part of his dissertation. I'd like to turn it over to Scott, who I understand will have some interesting comments to make about working with Randall. Scott, take it away.
Yeah, thanks, John. That's a hard act to follow. Yeah. So I'll, and it's a hard.
This is part I've been waiting for 6 years.
Yeah, see what slides are going to come up.
No, don't try to manipulate the process.
So for everybody that doesn't know, so Randall did his master's with me in a group, and then as he joined E-IPER, I continued on as one of his advisors. One of the routines that we have in my group is that when somebody defends, I get to have a chance to do the introduction. And that means I pick slides from as many people as I can find and select which ones I think tell a good story. So for Randall, there's a very rich story, and it's hard to distill it down to something that's not going to take up the entire hour. So I will go quickly. This one is, if you see on E-IPER, this is, if you just Google Randall Holmes Stanford, that's what you're going to get. So it's not really digging very deep. But I will talk about digging deep here in a moment. So Randall is going to be talking about groundwater. You don't see him very often with a hard hat and with, I'll show you some different scenes, also with a vest on, but he can do that, and he'll go and he'll spend all night, if it takes, to be on a drill rig while they're coring, and sit there and take cores 24 hours at a time. And he is one that fits in well with the well drillers, which is a talent when you're a grad student to be able to go and hang with them. So he has the look and everything, but he also can come back and give you the same look when he's in the lab doing his lab work, right? Okay, now the other part is that I'm gonna hold on that just for a second. So Randall also, though, can put on his cowboy hat or his farming hat and go out and hang with the ranchers, right? So the farmers and the ranchers, he can do that too. And he fits in, and so the song that you heard me playing earlier fits really well, not only with his family, but also with what Randall did. And so part of Randall's superpowers for his thesis work was the ability to go and embed with whatever group he needed to, including people who are not necessarily so keen on researchers, and go and build trust and find out that he could buck hay with them for a summer and build trust, and then find out what do they think about water and water management. Now, he also can be a real card at times, and you can see by scale here, Randall's a pretty decent sized guy, but he looks kind of small in this picture. That happens to be Johnny Kaspers, who was one of the starting offensive linemen for Stanford, who hung out with Randall as they figured out, using Randall's ingenuity, how to make a really, really cool calendar, right? And so, anyhow, Randall also can always tell a story. And so he can be the orator that people are going to come and come around, and you'll hear in just a little while, he is quite the spokesperson. So the other side, though, that if you didn't catch this, is that he is quite the musician and quite the accomplished musician, and not just the hobbyist, but actually is part of a band. And so I will say that he puts on these gigs, and you can go to Spotify and find some of them. So he is quite not only the bassist, but he is also quite the lead vocalist for Redshift. So if you ever get a chance, wait till Redshift's back out on tour after
Post-thesis submission.
Yeah, quite the thing.
Number 4 or 5 priority on the list.
Yeah.
But.
All right, so we'll also say that Randall's just been a phenomenal group member. He's the one that everybody looks forward to seeing, and always has for his time throughout our group. He's always one that we can count on for being somebody who is going to step up and do whatever is needed for the group to help encourage group camaraderie. He's just a really fun guy, and he's a super hard worker and a really great mentor. His biggest accomplishment during graduate school is not what's going to happen here in the next few weeks as he gets his thesis done, but it was his little guy that they had, so Julian.
That's right.
Yeah, so that's really one of the things that Randall has done over the last year is not only cram a huge amount of work into a short bit of time, but he's also done that while he's been staying up all night regularly, as you do when you have a newborn. So with that, I will just say that Randall has done really amazing research. He is just a wealth of knowledge, and he has done so many different things, too, that I think you're going to see what he brings to bear on the problem of water. And I think we should all watch for where it goes in the future, because Randall's just the classic rising star. So, Randall, I'm going to turn it over to you and let you talk about your research.
All right. Thanks, Scott. Good afternoon. Thank you all for being here. I'm really excited to share with you what I've been working on, not just these last 6 years, but the last 12 years at Stanford. This is just a slice of what I did as a PhD candidate in the Emmett Interdisciplinary Program over this last 6 years. But today I'll be presenting my PhD defense, which is titled Strategies for Managing Naturally Occurring Contaminants in Groundwater Basins of the Central Valley of California. And I like to kick it off with a greeting. So greetings. This is my defense. I did a little exercise with some people in E-IPER. I learned how to write 6 words at a time. And those 6 words, Midwest roots, Army boots, Stanford loops. Follow me. These are my Midwest roots. That's me with my little brother. These are my Army boots. That's me with my little brother in Baghdad. And these are my Stanford loops, 3, 3, and 6. So that's 12 years. There's a competition in the room. What I want to talk to you about today, when I think about California and its water system, I think about acre feet, and I think about the acre foot, And I'm going to tell you what that is because that's all I'm going to say this whole dissertation defense is acre feet. What does that sound like? A foot of water on a football field. Now, if you're used to European soccer, not American football, that's 2/3 of your pitch, okay? Those acre feet flow down thousands of miles of canals, and they're stored in really big dams. 50 million acre feet of dam storage in California. The rain falls in the mountains and goes into the dams. The snowpack melts slowly and goes into the dams. We have water all year long, except when the trees start to dry up and die. The ground sinks, the wells go dry, and the dams are empty. This was 2021. We are in a water crisis. We're in a water crisis in California. How can the dams be empty? Well, we had back-to-back-to-back years of drought, so there's no rain. The snowpack is going away because of climate change. So how many times do we have to deal with empty dams, right? You say, well, Randall, you just told me that the dams are full. What's the deal? Well, how long before we return to empty dams? And the problem with full dams right now is they're not going to sustain us over the next 4 years of drought. Most of the water that fell last year went off and went into the delta and is out in the ocean. That's what's represented in those two arrows. We have extreme rain followed by a whole bunch of drought. The snowpack, now if we get rain on snow, is really going to overwhelm our dams. So the system is broken. You're saying, well, just make some new dams. The problem is we've already built all the dams where the dams can go, and there's a lot of political friction to get that stuff moving. So where else could we store the water? If we need water all year long, we've got to store it somewhere. Where could we do that? Our answer is, let's store it in the ground. Let's use what's called managed aquifer recharge. We're going to flood some fields or some ponds and let it sink in. And just how much storage could we get in the ground? Well, I told you we have 50 million acre feet of surface storage in dams. Is this blue boxes, are these more or less than 50 acre feet? It's much more. It's 17 times more potential storage, maybe even more if we really get into this. That storage could look like a pond. This is a recharge basin out in the Central Valley. Or you could flood some ag fields and let it sink in. So in the future, is this what we're going to see? No rain, no rain, no snowpack, no snowpack, no snowpack, followed by really extreme rain? Probably. That's what's forecast. So we need a system in place that can provide all of these stakeholders with the water they need at the right price, and that requires a California system complete overhaul. California is working really hard on that. What we're proposing today is that if we can get that water back into the Central Valley and into the ground, then we'll have sustainable water supply. So my research motivation here is, let's face this water challenge in California. And I want to be part of the service, or be of service to the efforts dedicated to providing an amazing water resource system that provides water for all purposes and all generations. I want to meet our demand with a safe supply in the face of uncertainty. And I will work with California farmers to find out what they need and what they are willing to do for the water system. Why did I pick irrigated agriculture? They grow our food, and they're the biggest users in the valley. So I want to find out how farmers are approaching the water crisis. This is my research focus. I'll investigate what type of system could, even in the face of uncertainty, provide a safe and sustainable water supply that meets the demand of multiple users, including farmers. And I'll identify potential farmer needs that I am suited to address in the context of California's water system, reimagining process and collaborate on a useful tool that will be available for those who willingly support building an amazing water resource system for all generations. My dissertation overview, my first chapter was an introduction, basically what I just told you right now with a lot of details. The second one, I looked at threats to our groundwater from the farmer perspective. I wrote a chapter thinking about how can we balance quantity and quality. There's groundwater issues, right? There's a quantity issue and then there's a quality issue. And then I got to design an aggressive design scenario where we looked at economically viable and safe groundwater storage. I'm mostly going to talk about the second and fourth. So, threats to groundwater, farmer perspectives from California's Central Valley. My research objective here was to gauge farmer willingness to participate in managed aquifer recharge on their farms. I had several questions. This actually list used to be 15 questions that I boiled down to 3 for you. So how do farmers in the Central Valley of California make decisions about water in the face of hydrologic uncertainty? What do farmers perceive as the biggest threats to their water supply for both quantity and quality? And what would farmers be willing to do to support re-engineering the California water system? And what do they think their role is? So I went out and I interviewed farmers. I interviewed 30 in the Central Valley. 23 were from around Madera. 2 were technically in Fresno, but had farmed in this region that we know in the purple, known as the East San Joaquin Groundwater Quality Coalition area. I also interviewed a couple of dairy people from Turlock, and there was one almond grower / chicken farmer also around Turlock. So what this type of research is, it's called qualitative research. I go out and do interviews. What I can't do is say I have certain numbers, right? A quantitative analysis. If I went out and did a survey, I could say this many people said this. That's probably representative of the general population. So qualitative research isn't that. So I can't say, aha, we know how many people want to do this. But we can say with some degree, what is their motivation behind these things? That's actually some things that we tend to miss in surveys. So that's what I kind of went out. What might we be missing from these farmers? I want to share with you what the distribution of the farm sizes are around Madera. And that's important because you might see an average and think, oh, they're all big farms. You might hear a 1,000-acre farm average. You might hear a 500-acre farm. But actually, most farmers in Madera are under 200 acres. So what I did here is I split the groups up by 100,000 acres. So this less than 1,000 acres represents 100,000 acres approximately of the smallest group in Madera. And then this middle group, 1,000 acres or 3,300 acres is the second group that also has 100,000 acres of land. And then the biggest farmers, there's 14 of them that also have about 100,000 acres. How does that stack up with the rest of the United States? The rest of the United States has about, or excuse me, the rest of California, there's about 69,000 farms in California. So this is what, 1%? Not bad. I used 2 academic frameworks. I used what's called the Driver Pressure State Impact Response, or DPSR. Don't worry about the details yet. This is complicated, and I'll tell you everything you need to know. There's a lot of stuff you don't need to know right now. The other one that I used is a coupled infrastructure system. So to talk about drivers, pressures, states, impacts, and responses, what you're trying to do is put all the information you have into a framework so that you can communicate that out to people in society, or people in science, or people in policy. So what I did is I looked at the farms and I said, well, what do we need to do to define a driver? And I got completely confused because the literature was all over the place. Luckily, another researcher sorted it all out and said, this is what a driver is, and I was able to adopt it. And I said, all right, this is what a driver is. It's a driving force, is a superior complex phenomena governing the direction of changes in a coupled infrastructure system. If you don't know what a coupled infrastructure system is yet, I'll show you, just wait. That originates from either humans, nature, or both. So there's the whole definition. And I wanted to apply that to the farm. So there's a couple of ways that you think about farms. There's the stuff that the humans do and the stuff that nature or the environment does. And that's kind of how I split it up, the biophysical nature of these things. And that sort of split circles all the way around the DPSR framework. I posed this responses as a ring instead of the web, because I think that internal to the farm, they're all making these decisions for things that happen inside, not going outward or down. So it's a little visual representation that I thought was fun to do. What did I find out? Well, when I asked these farmers what they're willing to do, farmers were motivated by a passion for growing and the love of the industry. Quote, farmers are so passionate, they don't do it for the money. I'm gonna say most don't do it for the money, they do it for the passion, the interest. They don't wanna work in any other industry. It's just what their family did. They grew up doing it. They're hanging on. It's nostalgic, you know. And so I just personally want everybody who wants to keep doing that. I want everyone who wants to keep doing that. And so I just want to support farmers who care to do that. So for those who want to stay in it and be a part of it, I want to do my part to see that they have that opportunity if they choose to. So why did I give you that quote? It gives you the motivation for where these farmers sit in a really big system, right? So the coupled infrastructure system is something that I learned about in a sustainability lunch from Marty Andrews from Arizona State. And the guy had no idea what the guy was talking about, but I was fascinated. This is an image that I lifted from one of his papers. It gets complicated here, right? Well, the point of the coupled infrastructure system is that we don't necessarily operate independent of everything else, right? When I think about California infrastructure, I think about canals and dams. But when Professor Andrews thinks about infrastructure, he thinks about the relationships to one another. He thinks about the nature. He thinks about social interactions, and economics. So those are all considered infrastructure to him. So why do we put the farmer inside this system? Because they're related to it all. So that DIPSR framework is related to the farm, which is related to this natural infrastructure, which we're going to call a common pool resource. It's a water system, it's the surface water, and it's the groundwater. And when you get the whole thing, don't worry about the details. This is the complicated slide, right? Don't worry about the details. If you had to manage a relationship with every entity on this page, it would be exhausting. Am I correct? Well, that's what the farmers have to do. We haven't even shown you the biggest piece yet. So talking about groundwater, you also have to manage the surface, which is what they do when they're growing, and they have to manage this black box, which is biogeochemistry. So they've got a lot on their plates. And one of the things that they're concerned about with that box in the resource is if it's going to be here for the future. So I have a quote here for you. Well, yeah, I mean, you know, decisions we make, we want to be good, and as I said before, good stewards of the land. But also, we want to be, you know, friends with our community. So any decisions we make that will help the community and naturally really help ourselves, you know, it's a partnership, okay? It's not just about us, it's about people. So that gets into a question about what do they consider pressures on their farm? Well, what's a pressure? The formal definition is a pressure is a result of a driver-initiated mechanism, human activity or natural process causing an effect on any part of a coupled infrastructure system that may deplete, degrade, or otherwise cause deleterious changes to the state of the common pool resource. There are three other things on the slide. The states, impacts, and responses I'll brush over really quick. States are things you can monitor. Impacts are things that can go bad or good. So trees dying from lack of water, that's usually considered negatively. Getting a lot of water and being healthy, happy trees, that might be a good thing. And then there are responses. I'm mostly going to focus on responses to those pressures because that's what we're talking about mostly with groundwater. So what is the biggest threat to your water supply? I went out and I asked these 30 farmers, what's your biggest threat in general? And they came up with a few things. Supply is limited. We don't like the government, politicians, and Delta fish. There's too much demand and overdraft, too much pumping, it's out of control. Mother Nature came up, climate change. One of the things that was really fundamental was the price of water really bothers these farmers. And then not so much, and again, this isn't quantitative, water quality. It did come up though, so that's great. The one that was fun for me to sit in the interview was the one that said bad scientists and bad science. So that's out there too. And then I asked these farmers, what role should managed aquifer recharge play in reversing overdraft? This is a response to a pressure. I want to get water onto my farm so that I can use it. Most of the people said a lot. Now this is actually a really drastic change from 10 years ago in a survey where they said not so much. And it depends on what kind of managed aquifer recharge you're talking about. But recall, we can't conclude the numbers are significant, but maybe the reasons are worth further investigation. And I had one farmer tell me, hey, the managed aquifer recharge thing isn't new. There was one of the best engineers we've ever had in the Central Valley tell us 30 years ago, we need to do managed aquifer recharge. Jim Provo was very pragmatic and he said, if you had 5-acre recharge basin in every 100 acres, you could maintain a wonderful balance. And you just keep that recharge basin full and clean out the silt every once in a while, and that would mitigate your groundwater recharge everywhere. But according to this farmer, people don't believe that stuff. But I mean, Jim, he was right, and you can do that. So we went out and asked, hey farmers, if you were going to do this recharge, given that high magnitude flows come every 5 years, how likely would you be to build your own dedicated basin, just like Jim Provo just talked about? Most of them were likely. A couple of them that were unlikely because they wanted the irrigation district to do it for them. So this is really a different picture from 10 years prior, and what happened in between? 3 massive droughts, right? What would happen to water quality during managed aquifer recharge? Most people said it would improve. Okay, maybe that's fair. Maybe the stuff right below the root zone, if you're collecting evapoconcentrated salts, maybe that will dilute and get out of the root zone. But I'm not convinced that's the whole answer. Again, we don't really know what the motivation is. A lot of people said it depends. And then we got into some field work that Scott and I have talked about a lot, is What about naturally occurring contaminants like arsenic and uranium? We know that they're out there, but do you guys, farmers, do you know what could cause those to get into your water? Quite a few of them said not sure, no clue. It's not a concern around here. There was one person that did say they thought naturally occurring contaminants were a threat, but that farmer actually had a professional background in geochemistry. And I happen to know that if you have studied geochemistry, like I have with Scott Fendorf, you think about geochemistry and water quality during groundwater recharge, because that's what I actually started working on when I came to his lab. One of my mentors, Sarah Fakhreddine, a fellow Fendorfian, worked on groundwater recharge in Orange County, and they had arsenic in their water. And if you're thinking, well, how could Orange County have arsenic in their water? Well, that's what Sarah figured out, and she figured out how to keep it out of the water. So we've got to think about this now. Given that we know that there's an interest in managed aquifer recharge, California has a water crisis, there's a possible gap in considering naturally occurring contaminants, I went on a thought experiment and got really aggressive with managed aquifer recharge. So what did I do? I made an aggressive design scenario as a case study where I wanted to show, hey, is this going to be economically viable and is it going to be safe, right? So is it at the right price and is it going to be safe once we take it back out of the ground? So the research objective, provide willing farmers and water managers ideas for how to implement safe MAR at scale. If I say MAR, that's managed aquifer recharge, and I'll put $1 in the jar. And the research questions, what if we treated groundwater storage like a big dam? How much would that cost? And how could we provide management strategies to support safe water quality and a large, relatively speaking, quantity from managed aquifer recharge? Well, what's it going to take? So there are 11 critically overdrafted basins in the Central Valley that the Department of Water Resources has said, you need to fix this now. So they all went out and they made plans. They said, we're going to make sustainability plans and get sustainable by 2040. And what was in their plans? 79% was supply expansion. These are from the Public Policy Institute of California. So that's 972,000 acre feet per year that they have to get into the ground through recharge. And I said, well, I don't like that weird number. I'm going to use 1 million acre feet because it's easy. Let's give them a little extra. So we said, just round up. There's our big surface dam. It's 1 million acre feet. What does that look like? Looks like a surface dam, right? There's your surface dam, okay? What if we just cut it into 2,000 blocks? That's still 1 million acre feet, right? So you take those 2,000 blocks and you put them into pits like this. You excavate them, make them 10 feet deep. You have 500 acre foot pits, right? In wet years, we fill the basins, and the surface water becomes groundwater storage. Now, this gets into a political hot button item that I used to just punt on. All of the water that we need to put in the ground right now for the people in the southern part of the valley is in the northern part of the valley. So how do we get northern valley water to the south? I don't know, and I'm not going to give you an answer. But I do have a second scenario. Just this year, we had 5 million acre feet come into the South Valley from 13 atmospheric rivers. And that's 5 million acre feet above average. So I said, well, could we use 5 million acre feet, not just 4? Can we get 5 million acre feet of water into the ground? And here's the catch. You have to do it all in 120 days. Can we do it? Is that a lot of time or a little time? It's not very much time. So we said, yes, we can do it. We're going to put 5 million acre feet in the ground in 120 days. Well, how much is that going to cost? Did a very simple analysis. I thought about, well, what are farmers willing to pay? They can pay, with as deep as the water is now, $90 per acre foot to pump it out of the ground. Some people are paying $200 for an irrigated acre foot from their irrigation districts. Some people are paying as much as 1,100 acre foot just to keep their trees alive in severe drought. This year's flood release, they could get water for $10 an acre foot. It's very cheap. It's almost nothing, and I didn't include that $10 in my calculations now. All right, so a simple analysis, we use capital recovery. Capital cost recovery includes the interest, so you look 50 years in advance, that's a standard number. We're gonna have this pit for 50 years. I actually think that's short. You dig a hole, it's there for a long time. You dig a dig hole, it's there for a longer time. So I actually think you could probably use this pit for 200 years or maybe 1,000 years. It really wouldn't be that big of a deal if you're maintaining it, unlike a dam where it's cement. Anyway, so the the cost per year is that 2.5408. I'm going to carry that number forward to tell you the annual cost divided by how much water you get over the lifetime, right? So you get a 5-year number, you divide it by the 5-year price. Does that make sense? And you end up with a number, and that number is in bold. These scenarios, the first one, is only 1 million acre feet every 5 years. That's not even breaking even, and it's at 424. But if you can get all 5 million acre feet every 5 years, you're at $200, which is exactly what the farmers are willing to pay. So it's economically viable. Now we have to decide where to put them. Where can we strategically decide to put these things so that they are safe? Well, lucky me, UC Davis did an amazing multi-criteria analysis tool. It's called the Agricultural Groundwater Recharge Assessment. And it's a multi-benefit MAR siting tool. They consider disadvantaged communities. They think about pesticides. They think about groundwater infiltration from another model that's called the Soil Agricultural Groundwater Banking Index. They wrap it all in there and they say, let's put all of our water here, right? I'm like, yes, this is great. I don't have to do all that. You know, I can augment this perhaps with something that's useful. So the question is still, they only thought about pesticides, and what are we concerned with? We're concerned with naturally occurring contaminants. So if those pits are out there in the Central Valley, we still have to worry about something. And that something is the big pink box over there. I went through and I analyzed a bunch of other tools and said, all these decision support tools on the top 4 are actually managed aquifer recharge oriented. So how do they stack up against groundwater quality? SAGB is pretty much, it's almost all quality, it's almost all quantity with a couple of chemistry considerations for the soil itself. AGRA misses anything else on quality except pesticides. The Recharge for Resilience is that R4R abbreviation from Environmental Defense Fund. They looked at nitrate. And then the Community Water Center is not a MAR siting tool, but it does consider groundwater quality, especially for drinking purposes. So then if you wrap up all the other tools that California Department of Water Resources is looking at, they've done an amazing job. I picked one of them to think about, and it's called the Aquifer Risk Assessment. So the Aquifer Risk Assessment is something that I'm going to pull forward and say, we don't know what we're doing with naturally occurring contaminants because we don't have a tool that can predict where they're going to be. Well, I got lucky because I got to work with Alondra Lopez to figure out how to do that. So we came up with a tool that's using random forest modeling or random forest classification, where you come up with all the parameters. We know a lot of information about the stuff in the Central Valley. We know what concentrations of different chemicals are. And we said, well, all things being equal, if we could come up with a predictive model and say, well, we know what the conditions are, what's the chance that that place with those conditions will have arsenic or uranium? And this model did a pretty good job of that. And at the end of Alondra's PhD, she used layers that look like this, like soil coarseness and where that water is in the depth of the ground. You stack them all together and say, aha, we know the probability of getting arsenic and uranium in the water. So what you're looking at here in the yellow are basically danger zones. There's a high probability that you're going to end up with arsenic in the ground. There's 4 plots on there because we used public supply wells, which tend to be deeper and better monitored, and there's domestic supply wells, which tend to be less well monitored and shallower. So we did all that, and we thought about it, and I even made an extra model to look at the north and the south and different predictors. We're going to skip over that and just put it to use. So we have arsenic in pink, uranium in yellow, and then the Department of Water Resources Aquifer Risk Map there on the right. We stack them all together. We look at the overlaps, and we say, how does this little area that's shown right here stack up with the UC Davis tool? UC Davis, if you put all those contaminants together, right, our layer in the orange is all the contaminants, and the blue dots is the AGRA. There's a lot of blue dots underneath the orange, if you agree with me or not. I think that's interesting, but I would not want to be drinking water out of this zone because I have arsenic to my left and uranium to my right, and they're overlapping in the middle. And that doesn't even include the Department of Water Resources Aquifer Risk Map. So I said, well, but they're not all covered, right? There are still some blue squares out there that might be safe. So I said, well, let's highlight all the contaminants and see how much room we have left to actually do this thing. Where could we use that doesn't have a known threat right now? That's this area. So how much AGRA can we use for AgMAR versus dedicated basins? And what you're looking at this chart is, to direct your attention all the way over to the left, 3% of the AGRA is in non-threat zones, right? So we can use 3% of the agra. Good job. What does that translate to in actual managed aquifer recharge? Does it get us to 5 million acre feet is the real question. Do we have enough area in the agra to get 5 million acre feet in the ground? And the answer is no, we do not. It's unfortunate. Even worse, catastrophic failure. We don't even have enough room to put groundwater dedicated basins in with the agra. So no matter where we go, we have to consider naturally occurring contaminants. If it's clean going in, it needs to be clean coming out. So we have to come up with some way of mitigating these threats. We don't want to be drinking arsenic. It's bad for us. We also don't want to be drinking uranium. It's also bad for us. There are many other contaminants out there, but I'm going to focus on just those two. Since we're recharging by infiltrating through the surface, right, I'm going to go through a triage of what to pick first. I don't want to pick things that are overlapping because it's much harder to deal with, right? Don't pick two, pick one. I'm picking arsenic. Why? In geochemical terms, arsenic is better to manage from the surface because we can assume that it has oxygen in the water. And arsenic doesn't really like oxygen. So we're going to say infiltrate it with oxygenated water. Make sure it never loses the oxygen. That's the key part of this mitigation strategy. Farmers know about this because if their water goes anoxic or loses all the oxygen, it kills the roots on their trees and the trees die. So they're actually pretty good at this. They have sensors, they can figure it out. The other part is you also have to keep the acidity low. So the other mechanism that arsenic will get in the water from is if your acid actually goes basic, right? You go basic on the pH scale, you're going up. Keep your groundwater pH below 8.2, you should be okay. And farmers know how to do that too. Why? Because they use sulfuric acid as a conditioner on their soils. They're used to having to keep the pH down. So that's something that they can do too. But what happens if you're in a uranium area and you still have to recharge? Well, let's think about that. Uranium is a little bit trickier. It can actually get into the water when there's oxygen, so it likes to get out of the rocks that it's in when there's oxygen around. That's not actually that big of a deal because usually it just goes right back on the rocks. But when it is a big deal is when the pH starts to go up, starts to go basic. And that actually interacts with the whole carbonate system. So this is a very complicated system. I'm not going to get into the details, but if you look at where this red line sort of makes a really big arch in the middle, that's pH around 7.5. And the black line starts off down around 6. These are trace concentrations of what you call carbonate, CO3 2-. When those start to get in the water, even at trace amounts, they start to make these molecules that are really stable with uranium. They're stable, they stay in the water, and they don't want to get out. So we're saying keep the pH below 7.5, which farmers know how to do. So if we start there, we should be okay with mitigating at least some of the threats that are out there. There's one other consideration for calcium. Farmers add a lot of calcium, and there's a similar connection with mobilizing uranium and calcium. It's a part of the same molecule that drives this carbonate. So let's not put a lot of calcium on the recharge areas if we know that there is uranium. And that being said, we're going to wrap it up by talking about how would farmers approach this? How would we get a new system if we're worried about snowpack? We can use recharge, we can use irrigated agriculture, we can provide water for safe water systems for small communities, we can keep healthy ecosystems, we can have resilient urban supplies, and I think the one thing that may be missing here is keeping the delta charge. So the delta water is also another one that's pretty big. So we can do all of those things. And just to wrap up what I was talking about in my dissertation, I was using a community focus. So I went out and did interviews. I said, hey, let's balance quantity and quality when you talk about managed aquifer recharge. And then I came up with a decision support tool. So for my dissertation, I interviewed farmers, and I've come to understand the relationships and interactions within California's water system. It's very complex, especially for farmers. And I used the coupled infrastructure framework. And using DIPSR, the drivers, pressures, states, impacts, responses, I organized farmer decision-making with respect to quantity and quality. The farmers I interviewed want to be part of sustainable stewardship. And I confirmed there is a gap in planning for managed aquifer recharge with respect to water quality that needed exploring. So I wrote a chapter about balancing water and quality, quantity and quality. And I came up with some prices of water with dedicated basins and other management strategies, including dams. I looked at agricultural managed aquifer recharge. It may be less expensive, but the uncertainty around mobilizing contaminants makes thorough scoping and management problematic, as do operational needs that conflict with timing of managed aquifer recharge and hesitance to adopt it as a conservation practice. Nevertheless, some proactive management strategies such as thorough site reuse, and that is reusing the same recharge areas and limiting land area, can balance quality and quantity of recharge, and we can implement that to maximize recharge efforts. Lastly, in my chapter using an aggressive design scenario, I illustrated a network of dedicated basins would be economically viable for some farmers, dependent on the amount of water recharged. Managed aquifer recharge siting tools, augmented with random forest classification models, increase the safety of siting managed aquifer recharge, and managed aquifer recharge will inevitably or unavoidably have to manage naturally occurring contaminants. So proactive management strategies can mitigate naturally occurring contaminant threats when planning managed aquifer recharge. Again, I did 30 farmer interviews. I did a synthesis on managed aquifer recharge, and then I did an aggressive design scenario with simple economic analysis using geographic information science and random forest modeling. And I'll leave you with a quote from a farmer. "We need to capture this water, not only for agriculture, but for California, the state, for everybody." But I have a few thoughts about that. Collaborative work takes effort. A wiser person than me once told me, "Service might not make you rich, but it could make you happy." So we have a lot of people who are willing and ready. Let's go.
It was very communicative and entertaining as well, so I think we all appreciate that. So at this point, we have 10 to 15 minutes for questions in the room. Please raise your hand, and I will monitor questions from the online audience. So let's start with a few inside. Great. Okay, back in the corner. Say your name and then ask the question.
So the people that are not only use groundwater, and the people in the irrigation district have to pay a lot of money to be in the irrigation district. And those people are saying the people that aren't in the district are pumping all of our groundwater out from underneath us. So with respect to your question, who is in for it and who's not? The irrigation district, if you're inside it, people are actually pretty usually happy with them. They might call them lazy because they're not cleaning the canals fast enough or something to that extent. But most of my data is drawn from like Tulare Irrigation District, which top notch, really great to work with. I feel like most farmers trust the irrigation district to do the right thing. One thing that is interesting though about being inside the irrigation district, there are farmers in there that still don't use surface water. They only use groundwater. And they have their reasons, but it's an interesting take. When you're really, really water stressed and you're not using the surface water that's available, you kind of have to ask that question. Are you for us or against us? No, you're not going to go that way. But there are ways that you can implement things through NRCS or something to that effect, where you'd come up with programs to help them address that. Did I answer enough of your question? Why?
In many cases, like it'll probably be the irrigation district who's implementing a lot of the solutions and forcing that upon.
Yeah, there's a whole other topic we could talk about in terms of Sustainable Groundwater Management Act that came out in 2014. I glossed over the details on that because that's a study on its own. But the Groundwater Sustainability Agency is another place that you're supposed to be able to coordinate that type of operation. And the word on the ground from a lot of these people, and a question I asked in these interviews is, do you think SGMA's going to fix this? And they basically mostly said no. SGMA's not going to help. The problem with that, if you're thinking, well, we'll just take it to court, California says if you take it to court, we're going to use all the people that came before you as examples, and you're going to end up splitting the water anyway. So we're probably not going to see 20-year litigation over groundwater resources again. Buzz Thompson over in the law school will tell you, as a water czar, you end up splitting stuff.
Yep.
Hi, my name's Jeshna. So I had a question because the part of the map where you showed the overlap with arsenic and uranium,
Yep.
there was like a little corner that showed Tulare. Was that like the lake that came back?
That is a great question. So Tulare is a lake, but it's also a city. So I should have been specific. That's Tulare, the city. In between Tulare and Corcoran, there's a place called Okieville. That's actually somewhere that Helen Dahlke and who's the co-author? The last name is Marwaha. They have that exact plot in their study saying, let's do it here. And I said, we want to think about naturally occurring contaminants. I'm all for doing it, but we have to do it with these considerations in place. That's, I think, one of the big takeaways. We're not saying don't do managed aquifer recharge because it's there. We're saying do it with a mitigation plan in place. So.
A couple of interesting online questions, I think, related to the first question from Natalie E-IPER. Who should be responsible for building the infrastructure you recommend, the farmers or the irrigation districts? That is.
So if you go back to my coupled infrastructure systems diagram and take my quote from the farmer at the end, we're all responsible in our own way. And where I would see the farmers willing to be responsible, they're going to take their 1 to 5% and say, all right, I'm going to reinvest this into my farm. Now, what do the cities do? Are they reinvesting 1 to 5% into their cities? I think working with Dick, we would say it's a lot more than that. The problem is going to be in how much water is there. So who's responsible? Ultimately, it's going to be the state that's going to be overseeing a lot of the things. So the state of California has the Division of Multi-Benefit Projects now, where if you're not providing drinking water, if you're not providing ag water and a bunch of ecosystem services all at the same time, you're probably not going to get funded from the state. So who is responsible? We are, but the state's going to be overseeing it.
So a question from Quentin Lewis. Why was it important to do the interviews with the farmers to get at their motivation, given all the effort that it took to do so? So from a policy standpoint, why did you feel that was an important thing to investigate at that point in your work?
It's a good question, Quentin. Quentin went to high school with me, so he's my informal mentor on the side where I can cry. So I did interviews because I felt there might be something that we don't know. And we don't know what we don't know. So when you go out and talk to a farmer, he might or she might have a completely different perspective. Hey, you're in the irrigation district and not using surface water. Why? Well, it's too troublesome. We have a crop that's really, really sensitive, and every time we used the surface water, it killed everything or brought in a disease. So most of it is that qualitative information. It's rationales for why you do things. It's much harder to get that in a survey, in my opinion. And if you do put it in a survey, it's probably an open form answer, which to me still ends up being qualitative. It's hard to get that kind of information. I would now take that and try to make a quantitative survey and say, hey, now we need 5,000 farmers. What do you think? That might be representative of the population. But the qualitative part is, are you willing to do it? Yes or no. It's really the why. Why would you do it? And under what conditions? How can we help? Those are the kind of things that I was driving at, that I felt like we didn't really know, and I had to talk to a farmer to get it.
Great. One last question online from Lihi Yona, who you probably know.
Say again?
Lihi Yona.
Oh, yeah.
Yeah. So that you probably already know the question.
My writing accountability.
You probably already know the question. So it seems like it was a lot of effort to put your information into the DIPSR framework. Mm-hmm. Can you talk about why you chose to go that way at that point in your story?
So one of the things that I tried to do as an academic is follow other academics. The DIPSR actually had come up before me with my collaborator, Courtney, who'd also use the DIPSR framework. So I'm like, no problem, easy peasy, DIPSR framework, knock it out, it'll be easy. And then it wasn't easy. But I'm not the only one that suffered that. So that's ultimately why I took it. It was something that I was collaborating. One of my collaborators, who was already down the road a ways in her career, had used. And I'm like, well, we should do that again. So getting common frameworks to compare across different geographies and around the world is also something that, like, the coupled infrastructure system is trying to achieve. If you're coming up with academic answers, it'd be nice to be able to know that when Gabrielle goes out and does the same study, we can compare them and say, there's something here, or maybe we're different, but it's only different because the framework was different, right? So that's one reason why. But also it got into the reasoning, those drivers, like why are you doing what you're doing? I thought you were just in it for profit. No, I just want my grandkids out here. Yeah.
Great Q&A session, both the questions and answers. I felt. Now I'm supposed to turn it back over to you for some last words. Maybe some acknowledgments or some such things. Who knew?
All right. Buckle
Start
in.
with this guy here.
I told you 30 minutes on the presentation, but you didn't say about the acknowledgments.
Yeah, it was actually 33 and a half. I lied.
All right. Well, I want to thank this guy. Scott already pulled this picture, but yeah, my wife, Bora. Next month, we've got our 18-year anniversary. Thank you. Thank you. I love you. She couldn't make it today because she's with our little dude who turned 15 months yesterday. And he is absolutely amazing. I want to thank my committee, every single one of you, for being patient and saying, well, Randall, maybe there's not 1,000 things we can do. And Scott kind of got me down to 2, and Dick was like, maybe just do 1. Gabrielle was like, we're going to get this. It's going to be amazing. Just put it all on the paper. And it was like, so thank you, thank you, thank you. Christina, thanks for that early support. I really appreciate it. And then Sam Ying, I don't know how to thank you more. Sam was the one that sat me down literally in her kitchen and said, Randall, what's your name? It goes in that part of the form. And that's how I started my quals proposal. So thanks. I literally would not be in this point right now. And then John, it's been absolutely great working with you this year, co-teaching team. It's been fun. I love the capstone. I'll be on, I'll be on the E-IPER squad for a while, hopefully.
Yeah, we'll miss you next year.
Yeah.
But you have other fish to fry.
Yeah. Backing up a little bit, so Stanford wasn't my first college. Highland Community College wasn't even my first college, but my grandma got me to go back to college after my first sort of like weird adventure as an adult. I went 18-year-old old, I get up my scholarships for college and went out into the road with my brother to be in a band, and it was a tragic failure. Grandma was like, come live with me and we'll go to Highland Community College in Freeport, Illinois. I'm like, sounds great, Grandma. And look where I am now. So thank you, Grandma. And then there's my Midwest roots. It's my dad's 70th birthday, which I won't tell you how long ago that was. There's my family today. And there's my mom on the right when she was very young. So thanks all the family. Man, and I have this huge thanks for Zach Ranch. Peter Stickles sat down with me in the back corner of a table in Fresno, and I was looking around, I'm like, man, there's a lot of contractors and engineers and consulting firm people here. He's like, who the hell is gonna pay for all this? He was like the one farmer in the whole thing, 500 people and Peter Stickles. So Peter Stickles took me out and gave me the rite of passage to become an adult by letting me bale my first bale of hay. So coming from Iowa, I baled hay, I can be an adult now. Not only that, but Bora and I flew back from Chicago the day that San Francisco shut down for COVID-19. The mayor said, we're shutting down the airport at midnight or something, and we had a flight to Bali at 12:05. And Bora was absolutely certain that we should get on that flight. And I'm like, I'm not getting on that flight. We don't know how long this is going to happen. You get stuck in a place like that. You don't know how long you're going to be there, when you're going to get out. So I said, I have an idea. Kathy has an open invitation to go hang out in Bishop. We can live in the cabin. And what was supposed to be 3 weeks ended up being 7 months, where I did all kinds of other crazy stuff on the farm, like setting myself on fire. Not really. Not really. Not really. Oh, Matt Angel. So this guy, you go read this article. He's the one that got me in the door, other than my street cred having baled the hay. Matt got me these interviews. He said, what do you need? And he got me in the door, and he said, good luck, young buck. So thank you, Matt. I can't wait to meet up with you again in a couple weeks here, see what you have cooking. And then all my 30 interviewers, these people are really busy. They gave me 90 minutes, 3 hours, even 5 hours of their time, which I didn't know was actually really, really a lot. A lot. So thank you. And then I've got my collaborators, Alondra, Sarah Fokker-Dean, she's now at Carnegie Mellon, doing great stuff. Ali Sherris, we got Bridget Gile, Caroline Reinhardt, and Henry Lai. They're both my undergraduate now. One's a co-term interview coders. Courtney Hammond Wagner, she was the one that helped me sit down and write this interview protocol. And then Claudia, biggest supporter, and thank you. And then Denali also was one of my surge students that did just a fantastic job looking at a lot of like sort of this open source data on farmers to give us an idea of like what is known out in the open. And it turns out she did it. It was fantastic, so great job. Fendorf Lab, I didn't have time to write down all your names, but you're all here, and thank you. Thank you for showing up and being supportive and putting out the social calls. Wong Perotti Lab, it's been fun. It's been really fun. Dick, I haven't been to your lab too much, but thank you. I know they're there in spirit. And then the whole Emmett interdisciplinary program. This was something that I really wanted in. I was in my master's program, and I said, Scott, I know we're talking about this hexavalent chromium thing. What do I need to do to get into E-IPER? He said, Randall, it's a great question. I think you'd be a great candidate. He said, there's this thing called SGMA, the Sustainable Groundwater Management Act. So I wrote my whole application on that. Scott said, I think he's a good candidate, and there I go. I'm in, right? Thank you. Anne-Marie, who else is here? Gabby, is I still here? I. Many people that came, Guang Chao for the lab support. I did a bunch of geochemistry stuff in the lab that Guang Chao has been there every step of the way, so thank you. So then I get a question, what's next for me? If you remember my 2 words, Stanford loops, where do I go from here? What's next? What could we be doing? I'm going again. I am going to be a staff lecturer at Civil, Liberal, and Global Education, teaching freshmen, or frosh, looking at why college? Why are we in college, right? And then there's some things in the middle and at the end, so yes, I'm in for another loop. And with that, I think I will conclude at 3 minutes after.
Great.